So for this problem, we have this configuration over here. So you can imagine this positive Q charge, and on its both sides you have two more minus Q charges at a distance from A from the positive Q charge, and then you have two more charges, both positive Q, and also at a distance of A from the charge next to it. And then you have two more minus Q charges. And this sequence just keeps on going on forever and ever to infinity. So the problem now is to find the amount of energy required per particle to construct this whole configuration. So Griffiths gives us this formula over here. So this formula gives us the total amount of energy required to construct this configuration, and it's equal to 1/2 times the sum of all the charges times the potential of the position where the charge is located at. So obviously for this configuration over here, this total amount of energy is going to be infinite because there are infinitely many charges. So instead of finding the total amount of energy, we want to find the energy per particle. So as you can see from this formula, each charge contributes 1/2 times its charge times the potential of the location where the charge is located at. So you can see that each charge contributes this much to the total amount of energy. So as we know this is going to be infinite, it's kind of pointless to find this value over here. So now instead we're going to focus on the amount of energy contributed by each particle. So we're going to find this expression instead. So in order to do this, let's just focus on this particle over here, see what we get. So in order to find the amount of energy contributed by this particle to this whole configuration, we need to find the potential of the point where this charge is located at. So we want to find the potential at this very point over here, which would be this expression over here. So let's just focus on finding the potential at this very point first. So in order to find the potential, you can see that the potential at this very point is contributed by all these other charges over here. So in order to find the total amount of potential, let us consider these contributions case by case. So first of all, let us consider the contribution by these two charges over here, these two minus Q charges. So the amount of contribution is equal to 1/4 pi epsilon times the charge negative Q divided by the distance, which is A, and then multiplied by 2 because we have two charges. So this is the contribution from these two charges to the potential at this very point. So now let's move on to these two charges. So we have the same formula, 1/4 pi epsilon. This time it's a positive Q charge, and then the distance is 2A this time. So you can see the distance is 2A. And once again, we have two charges, so to multiply this by 2. And then we do the same thing once again. So this time we go back to negative Q. And then we divide this by 3A because the distance is 3A. And then we multiply this by 2. And then so you can kind of see a pattern over here. So if I pull out the like terms, so you can see that all these terms, they have this 2 as a common term. They all have a Q, they all have an A, they all have a 4 pi epsilon. So I'm going to pull out the 2Q 4 pi epsilon A. And so you see we're going to get -1 plus 1/2 minus 1/3, and then the next term is going to be plus 1/4, and then minus 1/5, and then it goes on forever. So obviously we need to try to evaluate this infinite series over here, and then we can do that by considering the Taylor series expansion of natural log 1 plus x. So the Taylor series expansion of natural log 1 plus x is equal to x minus x squared over 2 plus x to the power 3 divided by 3 minus x to the power 4 divided by 4, and so on. So you can see if we substitute x equal to 1 to this expression, you get natural log 2 is equal to 1 minus 1/2 plus 1/3 minus 1/4. And so negative natural log 2 is equal to minus 1 plus 1/2 minus 1/3 plus 1/4, and all the way to infinity. And so you see that this expression over here, so comparing it with this expression, you can see that this is actually equal to negative natural log of 2. And so now we can plug this back into this expression over here. So the amount of energy contributed by this particle is equal to 1/2 times the charge of the particle itself, so it's Q, times the potential at that very location, which is equal to 2Q divided by 4 pi epsilon A times negative natural log of 2. So these 2's, they cancel out. So in the end we get Q squared, negative Q squared because of the negative sign, divided by 4 pi epsilon A natural log 2. So this is your answer. And if you go back to the original problem, Griffiths actually gives you a pretty similar expression. So he's like, the challenge of this problem is actually to find what this constant alpha should be. So if you compare this formula over here with the answer that we got, you can see that the alpha is actually equal to natural log 2. So alpha is equal to natural log 2. And one question you might be asking me is that in this case over here, we were considering the positive Q particle, and then we got this expression over here. So this is the amount of energy contributed by this positive Q charge. So how about for the negative Q charges? So is it the same? So the answer is it is indeed the same. So the contribution by the negative Q charge is actually the same as this one. And you can see that if you calculate the potential for this negative Q charge over here, you get something very similar, but instead of starting off with a negative, you start off with a positive. So you start off by considering the two contributions from these two positive Q charges. So you start off with a positive, and this becomes negative, this becomes positive. So this infinite series here, you get positive, minus 1/2, plus 1/3, minus 1/4, plus 1/5. So instead of negative natural log 2, you get positive natural log 2. And then if you plug this back into this expression over here, this potential over here will be different from what we had because we had a negative sign. But the charge will also be different because this time you'll be substituting a negative Q. And so in the end, the negative sign just goes back into the expression. So in the end, overall, you just get the same expression. So it's the same, so you get the same result whether you consider the positive Q charge or the negative Q charge as we've done here. So this is the answer.